Okay, wait. So, could you tell me the precise statement of what? Huh? Hmm. That is fine. So V is a finite dimensional vector space. Over what? Over R. Right, but that's right. But here we assumed, obviously, by default, we assume that whenever we say R, we mean R. Um, yeah, with the usual topology. And right, then all norms are equivalent. That's right. This is more than that. I would say this is all norms are equivalent. So that implies that they generate the same topology. Okay, but norms being equivalent is more than that. It also means that uh, any metric you put will be equivalent. All Cauchy sequences will be same in both those kind of things. But there was something extra. There was something else that was bothering us. I don't precise. Right, unit sphere is closed and bounded, and yeah. So if you right, correct. Mm, just a minute. Oh, right. It is closed and bounded. That's I agree with that. Yeah, with the usual topology. Yes, but no, that's right. But I think we were thinking if uh, if you take R with some arbitrary topology, yeah, but then there is then obviously we cannot say, but we had put some other conditions. Just yeah. Such that tau is means there is a norm induced from that topology is normable. Now what can you say about the unit sphere, right? Because and really the question came down to say asking uh, is R complete with this topology, right? So it was something like that, yeah. So I don't know if you have thought about that version because otherwise this is fine. I mean, unit sphere is compact with the usual topology. If R because if R has a usual topology, then V is R to the n, and then everything just follows. Is normable, and we yeah. Let's just uh, yeah. Let's just run the proof a little bit so that can be clear. So let's say that this is one norm, right? And this is another norm. Srijani, about this, I don't know, you were not there in that class, but you can see the statement is this is the statement, and this is obviously a non-statement, but we are just we were discussing this last time, but now we are just seeing like a kind of a generalization, if there is any interesting such thing. So let's say that these two are two norms on V, then their equivalence, uh, then equivalence of these two norms is basically like, this is sort of like maybe basically coming down to the unit sphere being compact, right? uh, right, and the unit sphere is of course V such that, no, wait, so the unit sphere we have to consider with which norm? Right, correct. So then you take the unit sphere with the two norm, and the two norm, but yeah, but what does it mean to say two norm on V? Right, so basically, no, so there is a problem bit. Mm, yeah, so let's see. S- Alpha and this. Mm, mm-hmm. Right, and right, that's right. But yeah, so but in this case, which norm are we taking? To just to define a function, one, okay, but but in this situation, then what? In this situation, like what which two norm are you talking about? The two norm, so the two norm on R, and right, okay. But so what is the two norm on V? Because yes, on Rn I know we have a two norm, but on an arbitrary vector space, yeah, right. Yeah, let's think about that. So how do you define two norm on a because we know two norm on a vector space. The goal is to interpret this thing as minimum and maximum as of a function. So we're just thinking about what should the domain be. Hmm. Hmm. Okay. Okay. So let's compare everything with this norm. Okay. But then what is the? How do you say that this is a function on the unit sphere with respect to one norm? Right. Hmm. That's right. But there is something more, right? You have to ensure that, yeah. But you have to ensure that you are taking into account all the values of v in that process. Otherwise, they don't know, right? Yeah. Yes, and that's why I'm thinking. So when you normalize, then right, right. But the unit circle depends on the norm. What is a unit circle will depend on what is your norm. No, I mean that I assumed intention that you can prove. Yeah, that is true for all norms. Hmm. Yes. Yes. Hmm. I'm just thinking. Yeah, just a minute. Okay. Right. And then you want to go to Rn. Uh, uh, mm, mm, right. Okay. Okay. And then you define the one norm, two norm. Then you can define. Right. Yes. So when you if you fix a basis, then it's essentially considering it as Rn in some sense. But right, that's the same thing. Hmm. So okay, I mean that's but that is not going to create much difference. Even if we just consider this to be Rn, let's try to. So we're just taking the vector space as Rn. Okay, and now you try to prove. Let's see. So let's say the two norm is the usual two norm, and I know you want to. Yeah. So you think about that. Let's see. I mean, but I think it should be possible through this also. So yeah. Hmm. Yes. Yes. Basis. Yeah. Mm-hmm. Mm-hmm. Uh-huh. Okay. Which inequality? With this inequality? Okay, let me write it on a different page. Okay, you say the inequality. Mm-hmm. Right. Mm-hmm. Greater than or equal to? Mm-hmm. 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 Mm. Sorry. Mm. X by norm x2. Mm. Yes. Right. That implies cons x with 2 norm of x equal to. Right. And then you are then it comes down to saying whether the unit sphere is compact. Right. Yes. This is correct. So this is the I think which we were missing. And so here also it's the same thing. Uh, yes. Right. Because so the thing that we were missing is that if you have a norm, then this is equal to this. And so yeah, so if you take lambda times a vector, this lambda comes out uniformly for both, and then it just gets cancelled. And so it means that for this function, the range is gotten by restricting v to the unit sphere of any one of them. Yeah, of any one of the norms. Okay. Yeah, this is a point it came to me just before. So, but yeah. So I mean, I was missing it. So for some reason, I was thinking that lambda comes out as lambda square or something. And then there was a yeah, but obviously that doesn't happen, right? These are norms. But the reason why it came because of something, I'll tell you later. Uh, yeah, yes. So there are things like so there are like these kind of things that happen. Like there are two kinds of things like this, and of course one of them is not a norm. Okay, but it is still something which is called a valuation. Like if you take like once I think I was discussing with you. So if you take a number and you return the power of the prime which divides a number. Okay. Periodical. But if you take the square, that's also a valuation. Okay. So, but not a norm, right? But so these kind of things happen. But the problem is that through this valuation, you can still define a topology. Okay. Yes, and so that was a bit confusing. But anyways, I hope now it is clear. Yeah, Srijani, is it clear? So it's what we yes, yeah. So basically, I mean, of course, it's a very classical standard thing, but somehow we were getting confused. But it's good that we have overcome great confusion. Yeah, it should have not come in the first place, but okay. Right. Right. So it really comes down to whether the unit sphere is compact or the yeah, and that's equivalent to whether the unit ball is compact actually. Okay. Yes. But then you see, all this is so okay. What about R have we used? That is really the question. Like, what do we need? What did we need about R in order for this to happen? Obviously. Hmm. Hmm. That's right. That's right. But you see, no, but the thing is, I'm just saying that the it is on this that we are taking R to be this with this different topology. The norm is landing in R with the usual topology. That is always there because it's why one can say why we consider norms to study things, complicated things using R with the usual topology. So that we are not changing per se. But when you talk about vector spaces or non-linear spaces, there you can change the field, and we do change the field from time to time. We even take finite fields and things like that. So there I am asking the question, uh, asking this question. So really you can think about this basically. If R, like basically this, if you have R with some topology such that it has a norm, then will the unit interval be compact? Okay. Does this imply that the unit interval? So of course, I should say that I said last year also that when you talk about this, I am assuming that is an ordered field. Okay, like R is, I mean, as a set, it is, and it has the order. But that's all. I am uh, because you see the least upper bound property can be stated without norm, right? That is just an order thing, right? So you can state that property, and then you can also say that it's a field. Now, what kind of topologies can you put on it so that it is still normable, so that it's still that topology is still coming from a norm? And then can you say if the unit sphere is compact? If the unit sphere is compact, right? If the unit sphere is compact, then you can prove that in Rn the unit ball will be compact. That you have to use some things like product of compact sets is compact, things like that. Okay. So it really, the question really comes down to this, and we should think about basically what are all the norms that we can put on real numbers. Okay. Yes, right. And it may turn out to be not such an interesting question, but that you can see if you think. Okay. Yeah. So yeah. So let's then leave it at that, and yeah, let's move on. Yes. Okay. Okay. That's okay. Mm-hmm. 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 So. Mhm. Okay. Hmm. Hmm. Okay. So for countable, what do you do for countable? One, two, three in different sets. Like all singletons. Uh, s- so that's a countable antichain. Hmm. 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 Okay. Hmm. Hmm. And the other way around. No, you need both. Hmm. Hmm. Let's say S1 S2. Okay. Hmm. Hmm. You will get a new element Y. Hmm. 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 Yes. But then so what? So what? No, but you have I don't think you have shown that you will get for every comparison you will get a different element. That is a heuristic, like not even a heuristic, I would say. Yeah, something like a uh, and you get four different things. Okay. S- that sounds correct. So this is like someone Putnam question, right? Which once we were doing. Yes. Okay. Yeah. Okay. Okay. You remember the question. Yeah. Yeah. Right. Right. Something like that. Okay. Wait. Hmm. So that's fine. That's not a big deal. P of R will contain an uncountable antichain. Okay. That's also fine. That is okay. Uh, oh, how do you show that? Can I write your claim once? Yeah. Claim. Okay. Okay. Hmm. Hmm. Commas are fine. Okay. Okay. So that's what I have written. Open it up. Hmm. Hmm. Huh. Hmm. Yeah. So based on the position, because that will basically be a partition, right? So basically, um, okay. And yeah, right. Yes, and because there are uncountably many numbers, so you'll have. Yeah, so basically you are just looking at, you're proving that there are uncountably many partitions. And but this is the direct way to do it, which you are doing, right? Okay, that's fine. But you want one uncountable antichain. Right? It might actually be possible that it exists. I think. Why not? There's nothing that suggests that it's not possible. Right? Because there is that one of those theorems, right? That size of the largest chain times size of the largest anti-chain is okay. But that is less than. Yeah, is less than or equal to size of the poset. But that is, yeah. So that's maybe I suggest you people should think about it. So if you take an arbitrary poset, right, and then if you take the largest chain, right, and you take the largest anti-chain, so I'm not drawing lines between them, then the product of this size is obviously less than product, means you have to still prove it, but it's believable. That is less than size of the poset, less than or equal to. And it's quite not very difficult to believe, but you prove it, yeah, maybe. So that suggests that there is, because the largest chain is of course the countable, because that's just the natural numbers themselves. No. Uh, largest chain means okay. So you're considering power set with order. This is the poset, and this is basically anti-chain with respect to that poset. Right. Now, right. And then what is the largest chain? I suppose it is just countable, and that's just the natural numbers. You cannot have a larger chain than that, right? So that's countable, and but that doesn't really say if the largest chain is uncountable. Yeah, unfortunately, this theorem doesn't say that. It puts an upper bound. I mean, yeah, if yeah, yes, but so this is some sort of an infinite version of that theorem. Sorry. Let's imagine what it can be. Hmm. Right. I agree. Yes. 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 That's right. Why? Yes. 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 Hmm. I agree. Yeah. Hmm. So there is one uncountable set which I can think of, but it is actually quite different from an anti-chain, which is actually you would know this. So you take the rationals, which is same in bijection with Q. We can yes, we can do that, and yeah, once you have a bijection, then you can. Oh no, but yes, huh? Mm. We should be done because uh, yeah, because you just so the bijection with Q to N, right? You can use that to take subsets. Yeah, I mean the inclusion will be preserved under bijection. Is that of course it will be. So yeah, so it's fine. Yeah. Uh, Because I was just thinking because this where there are well-known facts, right? That there are no order preserving bijection and things like that. But of course, inclusion is preserved under by bijection. Preserved, right? So yeah, so work with Q, but then you see Q has an interesting uncountable set, but it is very different from an anti-chain. Basically, you take the Dedekind cuts, right? So right, and you take any alpha in R, And but yeah, and this actually I'm recalling the solution of that Putnam problem, and this is not my creation. You now you see. So yeah, so you take P by Q such that supremum of whatever such that P by Q is less than, yeah, the Dedekind cut corresponding to, yeah, and right, lower cut, and this is of course uncountable, but this is very different from an antichain. Two things, right? The indexes are and it's uncountable, and but it is a chain. Wait, oh wait, right? That's good, but it is a chain. So there is an uncountable chain. So I was wrong about that. Then how come I said that? Ah, wait, something is wrong, right? If this has an uncountable anti-chain, uncountable, so is this a chain? Yes, because given any two, one is contained in the other, and right, and certainly this is an uncountable set. So there is an uncountable chain. So it means there is some magic somewhere that has happened. So now if we take the bijection with that, yeah, that is what we are getting, but cannot happen. Yeah, but I suppose yes, because if you just take a bijection with, right, yes, uh, yes, because it will be contained, right? So if a alpha, right, so we take a alpha and then we take f of a alpha, and of course, if a alpha is contained in a beta, it of course implies that because it's just a function. And oh, so that was completely wrong what I said. So it has an uncountable, it has an uncountable chain. I don't know. Yeah, it suggests points in that direction, but yes, yeah. I mean, I'll just keep thinking about it. I mean, and yeah, it's very strange because if you have a finite set, let's say set of size three, then there you cannot have a chain of length bigger than three, right? Because you take one comma two, one a chain, right? You cannot have a chain of size bigger than three. But, tell me, you cannot have it. It has to contain one, but that's fine. That just increases by one. That's not a mistake. Okay, yeah. So, but suddenly when you have naturals, then there is a uncountable chain. That is quite strange, but it is true. Yes, yes, it's true. Okay. So then there is one more theorem, right? There is this Dilworth's theorem that's the following. So yeah, so decomposition. So P be a poset, finite poset. Now if you decompose P into chains, okay, and then you say number of chains. So number of chains in a decomposition, okay. So this is a chain decomposition, right? The number of chains in a chain decomposition in a minimum chain decomposition means you take your poset and you break it into, decompose it into, partition it into chains, okay. And then if you do it in the minimum way, then this is equal to size of the largest antichain, and that's also clear from the picture, right? I think, yeah, this is called one of there are few theorems like these. Dilworth's theorem, yeah, this will be it. Oh, these are all theorems in graph theory, so you can, or posets, whatever, easy to prove. But okay, now let's just I mean, if you are here, you means you can just think, or you can think about this later also. uh, what is the infinite version of this? And we can imagine what it can be like, yeah, like the cardinality. Yes, size of the which is what you are interested in. So this is the theorem that should have struck me first, but it did not. Because I was looking for the easier statements. Yeah, but this is the statement whose infinite analog we should imagine. Hmm. Yes, that's fine. But if you but it's, I think, directly if you just take, so there is a chain decomposition of naturals which is countable, right? So like one, two singletons, that's actually a chain decomposition. That's actually a chain decomposition. So if the infinite analog of Dilworth's theorem is true, then it means that the largest antichain has to be countable. Yes, and that's a decomposition. So a minimum decomposition will be lesser than that. Uh, right, right, right. No. Yes, right. Yes, yes. Oh no, wait. No, 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 no. What I said is wrong actually. So that's not a decomposition, right? This, because we're not decomposing natural numbers. You have to decompose the power set. Sorry, that was a very bad thing I said. Yeah. uh, yeah, but maybe you can think about a way to decompose the power set into chains. And if you can get in a countable way, you don't have to even care about minimum. If you just do it in a countable way, then that's it. And then try to cook up proof, look at the proof of the finite case and make the proof of the infinite case. Right? Yeah. Yeah, you can think about it. Yeah. Yeah. Yes, so like the Schroeder-Bernstein theorem that we once did, that's a finite version is there, but the infinite version is also there. And the proof is not difficult. It's graph theory, just some backtracking, some, yeah. So, yeah, I don't remember the proof, but it was not difficult, you saw, right? There was not any stress. Yeah. Okay. Yeah. So, yeah, think about it and also look at these theorems. I think you can come up with something interesting, right? And these are all, yeah. Yeah, yeah. Yes. Sure. Yeah, sure. Yeah, so we could not do it, but maybe, yes. Uh, Sujini, should we just try this for some more time? Is that fine? Or or do you want to, or maybe we can think about this later, right? Yeah, means that I'll just, because we have spent some time thinking about it. What do you think? You have any? Uh, Maybe you should also think about it if you want. This thing is quite interesting, but yeah, right. So yeah, let me stop this. Yeah, and yes. Do you want to discuss anything else? Maybe if you would. Right. Right. So, yeah, so now let us just, obviously we will not be able to prove it or anything. But let me ask you, so you are reading about the extension theorems, but maybe you could tell me the problems that you are trying to solve using it. And maybe with that we can say something. If okay, okay, fine. But that's then that's fine. That's fine. Maybe yeah, that's okay. So, mhm. Okay. That's fine. That's fine. Yeah, then we can just stop here, right? But are you clear about the statement of the Tietze extension theorem? That so what is the statement? So let's just take R, right? And then we can state it. Try to state it on R. So it's just that we have R, and it's an extension theorem. So you of course want to extend a continuous function.